join us, so forgive my halting speech pattern for a bit as I make sure to admit folks in from the waiting room and just manage Zoom on my end. But thanks for being here today. Be talking about hybrid ground source heat pumps. We've got a little bit of front matter, but looks like I've seen a lot of you folks before, so appreciate the opportunity to present again, albeit remotely. So you may be familiar with us already, but we are, if I can get my keyboard working, there we go, the Integrated Design Lab. We're a branch of the University of Idaho, the Art and Architecture Department, but we're actually a blend of architects and engineers. So we've got 3 full-time staff and 4 interns. And let me just admit a couple more folks. We just hired a new mechanical engineering intern, Jason Telford, who will be a grad student with us for a couple of years, so we're excited on that. One of our other graduate students, Lindsay Watkins, is she's taking finals right now. She'll be graduating in spring, so we'll be looking for another architecture RA coming up in the spring. So if you know of anybody that would like to have their tuition paid for and get a 2-year paid research gig, please let me know. We love hiring kind of new, passionate interns, training them on energy modeling and you know, building science, so they can kind of go out into the workforce and be a step ahead of the game. So yeah, keep us in mind if you've got friends or relatives that are kind of nearing graduation and looking at grad school, because we'll happily take them on. We do that through funding. A lot of our funding comes from Idaho Power, so we're thankful for them to be able to offer these CEUs and this time today. We've got some technical design assistance that we're able to offer. Like I said, we're grad students and faculty, so we're relatively cheap. And we've got 3 different phases of support where you can call our office anytime if you just have a random question about an energy efficiency technology. If it's up to $4,000 worth of our work, so doing a basic energy simulation or like an energy audit walkthrough, something like that, that's still completely free to you. Idaho Power will pay for that, but we just have to submit basically a 1-page scope of work to Idaho Power. If you want us involved all the way from beginning to kind of the end of the project, doing kind of detailed daylighting analysis, energy modeling, you know, doing a bunch of, you know, design charrettes back and forth, we love to do that. And Idaho Power will cover 75% of that cost. And then it's up to the client to pay the other 25%, but it's a pretty good deal. We're not trying to, you know, push any other consultants out of the way. Our goal is to actually teach ourselves out of a job, if you will, and increase the knowledge and skills within your own firm, so that after we assist you with a project, hopefully we'll have trained you on how to do that process in the future, so you can do your own, you know, daylighting analysis or lead review, what have you. All right, we've also got another lecture series, the Building Simulation Users Group. We just wrapped that up for this year, but we'll be coming out with new topics in 2021. So feel free to check out our website on those upcoming events. And we'll be hosting those via Zoom as well. So even if you're up in Ketchum or away from Boise, feel free to tune in. We also offer, through Idaho Power, the Energy Resource Library, about 900 different tools to diagnose your building, figure out if it's working properly, identify indoor air quality, light levels, pretty much anything you want. And we've also got documentation along with each of these instruments. So even if you haven't used one in the past and you're just like, hey, I need to know if this fan is working, how do I do that? Let us help. And we can ship those tools and those instructional videos to you. I think you pay for shipping, but otherwise Idaho Power provides the tools, training, all that. So feel free to look on our website for more details. And also just check out Idaho Power's website. They've got a lot to offer in terms of rebates on new construction, retrofits, some specifically about heat pumps, which I'll be talking about today. And if you're not sure if your project fits into that kind of scope, if you will, it's worth emailing them. They do a lot of kind of custom incentives as well. They're really trying to encourage energy efficiency so they don't have to build any more power plants, right? We want light, we want heat, we want power. We don't necessarily need watts. And so the more services we can get at a lower environmental impact, the better. So to that end, let's talk about hybrid ground source heat pumps. I'll kind of go over kind of the types, some of the advantages, and the implementation features. While Idaho Power support for us is primarily commercial, I know AIA Mountain, there's a lot of kind of high-end residential projects, so I want to keep that in mind as I present today, but please know that my background is more on the commercial side, but there's a lot of crossover between the two. So ground source heat pumps, not a particularly novel idea. Lord Kelvin came up with this back in the 1850s. At least he was the first person that we know of to document the idea, but it's basically using ground as a thermal battery, if you will. It's a lot warmer deep down during the winter, and it's a lot cooler deep down during the summertime. So if we can take advantage of that with a ground source loop, then we can get some more efficient equipment. So looking specifically at Ketchum, normally I'd be delivering this to you up there. I'm sorry I can't be. But you've got some chilly monthly air temperatures, right? So it just took the weather file, typical year for Ketchum, Idaho, and looked at the average air temperature there for each month, January through December. And if we were to look at the ground, just a 1.5 feet deep, if you will, it's even a little bit colder than the air temperature, but it gets a little bit less warm during the summer. As we drill a little bit further down, here we're looking at about 6.5 feet deep, and this is about the minimum depth for a ground source loop. You can see significant kind of mellowing of the trend, if you will. There's less extremes. And here we're just looking at, average monthly temperatures. But in addition, we're also avoiding those daily extremes that you'd see in the air temperature popping up and down. Ground temperature moves much more slowly, much more evenly, and keeps to this kind of general profile of closer to, between that 30 and 50 range. If we go even further down, looking at 13 feet deep, you can see we're really starting to, popular phrase today, flatten the curve a little bit, a lot less extreme than that air temperature. And that's really what we're trying to harvest using a ground source heat pump. All right, let me just make sure I'm welcoming people into Zoom. All right. So one way that we can heat up buildings is to just run, your traditional baseboard electric heater. You run electricity through a wire, the resistance in that material turns that into heat. And it sounds great to have 100% efficient system, right? You put in 1 watt of electricity, you get 1 watt of heat out. But this is actually a fairly outdated technology. And it's far more efficient to instead power a compressor that can then move heat. So all of us probably have some form of a heat pump in our house, whether or not we have a different furnace or air conditioning system, but your fridge is essentially a heat pump. And what you're doing is you're using that electrical outlet to drive a compressor. And by using 1 watt of electricity, we get to transport about 4 watts of heat. So it's, almost 400% efficient, or 4 times more efficient than just using an electric resistance coil. And it's not that we're, breaking the laws of thermodynamics. It's just that we're focused on moving that heat as opposed to just simply producing that heat. This is why the back and the top of your fridge is always, a lot warmer than what's inside. All right, so that's how a fridge works. How can we leverage that technology with, ground temperatures? Well, the great thing about heat pumps is that they are reversible. While a fridge pretty much only works in one direction. It's taking the heat out of that food and then moving it, out to the back of it and those coils. A ground source heat pump can actually be reversed. So during the wintertime, we are pulling heat in from the ground. And during the summertime, we're, pushing that heat back into the ground, and we're pulling up basically cool energy, if you will. And if you wanted, you could actually have, two different heat pumps using the same source, same ground temperature, but one could be in heating mode and one could be in cooling mode. Of course, they'd have to be on separate air loops if you want to do that. All right, so this is just demonstrating kind of, it's the same equipment, it stays the same. All we're doing is basically switching the direction, and our condenser, which was hot, then becomes our evaporator and is cold. And it's that beauty of that reversing valve allows us to use this technology in both climates, which is wonderful. All right, so just kind of wrapping up an overview of heat pumps. There's a lot of different types out there. VRFs, those are trending a lot these days. Variable refrigerant flow systems, those are basically a fancier version of a mini split heat pump. And a mini split heat pump is traditionally just an air-to-air type. You could even have a packaged rooftop heat pump system, or you have an air-to-water. A heat pump water heater is an example of this, or water to air or water to water. I'll be focusing on these bottom two today. And each of these names deal with where you're pulling heat from and where you're pushing it to. So in air to air, we're pulling heat in from the outdoor air and then pushing it to indoor air. Air to water, we're pulling heat in from the surrounding air temperature and pushing that into our hot water system. Today, ground source heat pumps, I'll be talking about, buried water coils. So we're moving heat from a water source into the air side of our system. Or we could link it with a hydronic system, a radiant system, and that might take an extra loop. So when we're talking about, the different loops that are involved with the ground source heat pump system, what's buried outside is going to be some sort of water, brine or glycol mixture, antifreeze basically, so it doesn't freeze up in the pump. And then this is going to be, this refrigerant line is separate from it, and that's going to be contained within the heat pump itself. So just kind of expanding on this, you've got your coils buried out here, or these could be boreholes. Then you've got a heat exchanger where you're exchanging heat with one side of your refrigerant loop. This is where your compressor is going to live. And then on the inside, you've got your evaporator coil, and that's what your air is going to be blowing across for the system. If we wanted to connect this with the radiant system, we end up with 3 different loops, right? So we've got one water glycol loop outside. This is basically contained within our heat pump. And then we've got another heat exchanger here to exchange with the radiant system. So looking at what that might be like in a building, we've got buried coils out here, our heat exchanger to our refrigerant, and a separate heat exchanger here to our hydronic system, which might be, in some PEX tubing within the floor. You can also do direct burial of the refrigerant line and have all of this as one refrigerant instead of having a heat exchanger. Haven't seen that as much in Idaho. Perhaps my experience is just limited, but traditionally what I see come across, at least in terms of design reviews, is water and glycol, and then a heat exchanger to the refrigerant that is simply contained within the heat pump. Let me pause here before I move on to check the chat window. I am notoriously bad at checking the chat while I am talking. I will leave time at the end for questions, but if you have a question, please know that I'm probably not going to see it until the end of the presentation. So just unmute yourself. I'd love for this to be more of a dialogue if possible. All right, so that's kind of, our overview. So how can we extract heat from water? What different types of ground source, or sometimes referred to as geothermal heat exchangers, can we get? The terminology gets a bit fuzzy, especially here in Boise, where we've got those hot water resources, which is true geothermal, where we're pulling hot water out of the ground. I guess Ketchum also had a geothermal district back in 1929, which I wasn't aware of till I was prepping for this presentation. But that's neat. But what I'm focusing on today is not necessarily hot water in the ground, but just ground source or ground temperature water, which is traditionally kind of, I'm calling ground source heat pump. But if you look online, like energy.gov, EPA, they'll sometimes use just geothermal generally to not only mean hot water resources, but also just anything pulling from the ground. So pulling that from the ground either in an open loop system, so we've just got a well of water or a pond, or a closed loop system. Closed loop, we could have horizontal coils, we could have vertical boreholes, or we could have it embedded in a lake or some sort of hybrid system. I want to start by talking about open loop systems. There is currently an Idaho Power incentive on these systems. I believe it's a $500 rebate. And these are great if you have access and if local codes allow you to access, say, a body of water. You know, if the water table is particularly shallow and you have, you know, the discharge and reinjection capabilities within that area, it can be a great solution. It's one of the cheaper ones. However, it can have higher maintenance costs because this water, initially it needs to be filtered so that it can go through the heat exchanger. And even with that, sometimes the minerals can foul up the heat exchanger a little bit. And so every 3 to 5 years, you might need to run a decalcifying agent through the heat exchanger so it doesn't clog up. I believe that was the issue here in the building where I am right now, where it was initially an open loop system, and it ended up not turning out for the best. But if you do have access to this, it's great. You have to work with a hydrogeologist to make sure that you do have the proper flow and the head on your pump to make sure that you can get the capacity that you need out of this. But because we're just kind of discharging and relying on a large body of water, you don't have to worry as much about, you know, running out of capacity, especially if it's, you know, very, you know, free-flowing water, like out in Eagle where they have a high water table and a lot of, you know, water kind of passing through. They're not necessarily worrying about overloading, say, this pocket of water. So that's one option. Next option is also a closed loop system, a horizontal ground loop system. So these are big slinky coils of PEX that can be rolled out. It requires more area and more piping, but they don't need to be buried quite as deep. As long as you get below 6 feet at least, or down to 10 feet, might be even better if you have the ability to do that. Then you're still taking advantage of, you know, the thermal battery of the earth, if you will. They can be installed vertically if you have worries about like interrupting landscaping in a 6 up to 24-inch wide trench, and then you can just resaw it over the top. Capacities on this might be a little more limited than, say, an open excavation site like here. You'll also see vertical borehole systems, and these can be up to 250 feet deep, fairly narrow pipes, and it's less piping material than the horizontal system, but because you have to rent a specialized drilling rig, it can be much more expensive. But you can pack these a lot closer together. So for example, in Boise, there was a case study, and it was about an 80,000 square foot office, and they were looking at putting in geothermal system in the parking lot area. Using a vertical borehole system, it was going to take up about 33,000 square feet. I think that was about half their parking lot. Whereas using the horizontal ground loop system, that was going to take close to twice that. It was going to take 58,000 square feet of coverage area. If you have a big open field, then great. But if you're in an urban environment, or you just want to rely on, you know, the more consistent deep temperatures, and you have access to renting a borehole driller, then it can be a great option. If you are set on a vertical system, it can pay for itself to drill a test borehole, just to make sure that your calculations on heat exchange and capacity are lining up. Otherwise, you might end up drilling too many or too few wells. Next, we want to talk about another system, which would be just dropping it into a body of water, in a pond or lake. There's a few of these around in Treasure Valley area, but I don't know how common they are. Certainly might be an issue if somebody is trying to have their personal trout pond. If this is going to freeze during the winter time, that can limit capacity a little bit. Or if they're going to be, you know, trawling a fishing lure through these and puncturing the coils, you don't necessarily want that. So these metal heat plates might be a bit better. They're also going to be more costly. And yeah, you know, talk with your engineer about, you know, capacity of, you know, whatever little pond this is going to be dropped into. So why use geothermal systems? You know, those things are looking like they might cost a little bit. The main reason is we're taking advantage of the Earth as a thermal battery. And by doing so, we end up with very significant savings for heating and for cooling, but especially for heating. You know, in Ketchum, imagine it's wintertime and it's 0 degrees. If you have a traditional air-to-air heat pump, you're trying to pull heat out of that 0 degree outdoor temperature and push that into, you know, 70 degree indoor temperatures. Frankly, it's probably not going to work all that well. It's going to switch into electric only mode. But even at, say, you know, 30 degrees outside or 40 degrees, trying to pull heat from 40 degrees and force it up to, say, 80 degree supply temperature for the indoors, that's your efficiency is going to be quite low, versus trying to pull heat from the ground in a very conductive medium, water, at, say, 50 degrees or maybe even 60 degrees, and then ramp that up to an indoor air temperature of, you know, 80 to 85 degrees as your supply temperature. Much higher coefficients of performance for your equipment. And by doing so, you end up with some pretty significant energy savings, reducing carbon emissions. This is, you know, big for lead now, as carbon is, you know, kind of one of those points. It's not just utility bill savings, and I know Blaine County has been looking at, you know, clean energy ordinances. So if you're trying to get rid of an old gas furnace, then a heat pump is an all-electric solution. And with Idaho Power going to a commitment of 100% clean energy by 2045, then this might be a motivating factor to use one of these systems. Also, you've got lower maintenance costs. Because we are dealing with kind of ground system, and then we've got in place our heat exchanger, the compressor doesn't have to deal with the, you know, high variations in outdoor air temperature, or even be set outside. It could be in a garage or sheltered in some way, because we don't have to be, you know, pulling that heat in from the air. Instead, it's just going to be going through that heat exchanger. So that means that outdoor compressor is going to last a lot longer than a traditional airside system would.
Excuse me, Damon, before you move on, I think Rebecca has a question for you.
Oh, thanks. Rebecca?
Hey, Damon, can you hear me?
I can, yep.
So I know of at least one system up here that was installed years ago that the pumps on the system used a ton of energy, and they were really disappointed in the performance. Can you address that? Is there a way to do that so that you don't have huge electricity bills from the pumps?
Yes, I will actually be getting into that in, I think, about 5 slides.
Okay, great, thanks.
Yeah. But yeah, great question. Thanks for bringing that up. Yeah. So yes, pumps can be a significant cause of energy use within these systems. Yeah, so I look forward to talking about that shortly. They can also be linked with your domestic hot water system and using it to preheat that. The underground piping can last anywhere from 25 to 75 years, based on what I could find from Canada's version of DOE. And the heat pump equipment itself is looking at kind of a 20-year lifespan. So when we're looking at kind of payback periods and costs, those are a couple things to keep in mind. So why not geothermal? Cost is especially initial costs can be a big barrier for commercial applications. If, like in Idaho, we've got relatively low energy costs, it can be a harder sell in terms of payback. And depending on the building function and your room outdoors to install a geothermal resource, it might not be the best solution. But there are situations where it does make sense, especially using a hybrid system. So looking at a local example, this was actually the Idaho Fish and Game headquarters. This was a commissioned study to look at the feasibility of using a ground source heat pump system there. They found that a conventional rooftop system for this building was going to be about $12 to $15 per square foot. The ground source indoor system, so these are the indoor coils, ductwork, distributing system, was going to be less than that, $11 per square foot. But you have to add on to that the cost of that extra ground loop. And that ground loop cost is going to vary not by square footage of the building, but by tons of capacity. So an open loop, they were looking at between $500 and $1,000 per ton. A horizontal loop, those slinky systems that can be spread out at 6 to 10 feet underneath the ground, those were $1,000 to $1,500 per ton. And then the vertical boreholes were $1,500 to $2,000 per ton. The highest energy savings came from the vertical loop because temperatures were just kind of more consistent there for that particular application. The system that came with the highest payback was actually the horizontal loop system, looking at that. But these are some things to keep in mind. And so while the indoor equipment might be relatively fixed, we still need fans, and people still need to breathe, things like that. What really pushes these systems over the edge in terms of price point is the amount of ground capacity that we're aiming for, the number of boreholes that need to be drilled, the size of the field, and the amount of slinky coils that we need for that horizontal loop. Even the design of the open loop system and the pumping that's going to be involved in that. So that's why I'm kind of trying to get to the heart of the design today, which is a hybrid system. So instead of just looking at, we've got really cold winters, let's size it to make sure we get the most out of it all winter long, you're going to be drilling a lot of extra boreholes. Instead, look at sizing the system on your smaller load, which in this situation would be your summer cooling. And during the wintertime, no, your ground source isn't going to be able to make up for that. It might fall short on a few of the coldest days. And so let's add in a boiler, an extra gas furnace, some sort of, storage system. In Arizona, we might be looking at a cooling tower or a small chiller or something like that to help supplement the cooling there. But here in Idaho, we're really looking at adding a little bit of supplemental heating. The thing is that the majority of the hours, our ground source heat pump system should work just fine. It's just those peak coldest days when our system is really struggling to meet. But if you look at 8,760 hours in the year, if we look at sizing our system to meet just say 60% of our peak, then the amount of equipment we have to install is going to be much smaller. And less than 3% of the time of the year will we be relying on kind of that worst case scenario. And that's where we can kind of upsize some of that supplemental equipment. So how do we kind of figure out where to draw the line? Really rely on, hourly analysis, not just rule of thumb, and make sure that you're not kind of oversizing the system, thinking that everything terrible is going to happen on the same day, of like everybody's going to be in the conference room at the same time, that all the lights are on the hottest day of the year. Look at how the office is actually being used to avoid adding kind of that extra safety factor. Safety factors are important, but if we add each one on top of each other, then we're going to put ourselves into a really tough financial situation. And then size the ground loop system on your non-dominant load. So here, size it to meet all of your cooling demand. And that's going to help balance out some of those soil temperatures, so you're not trying to pull, heat from the ground all year long, and it's never going to be able to catch up. We'll pull heat part of the year, and then part of the year we'll push heat back in. So it's going to stay a little more even. So you're not going to have that long-term ground temperature shift, which might actually affect your capacity for the system. By doing that, you can really reduce your loop size by 20 to 40%. And then if you do need, to satisfy that engineer with an extra safety factor, add that safety factor to the supplemental system. Upsize that boiler, the extra water heater, just a little bit more. It's going to be cheaper to do that than to drill extra wells or excavate more area. And then size the supplemental system for just the remaining load. Now, Rebecca, I'm getting to your question a little bit, so it was later than I thought, but let's focus on where that energy is going in terms of heat pumps. This was a study out of the Energy Center of Wisconsin, and they took a few different commercial buildings and looked at, where kind of doing simulation as well as installing the systems at these places and looking at, okay, over the course of the year, where is energy actually going? The supplemental system actually used very little energy, even though it could have been used for a lot more, like to meet those worst case scenarios. It looks like Tobacco Lofts, that apartment complex never even reached, never had to be tripped on for that particular year. And the indoor system, this is our, compressor or our evaporator coil or compressors, depending on which mode they're in, fans, all that. This is kind of this part of the system, but then we've also got to move all of that water and glycol system and glycol through our heat exchanger, through all that pipe that we buried in the ground. And that can be a really significant portion of the energy. It can be 20% or more, depending on the design of the system, of how much energy is being used there. So one kind of aim is to make sure that you've got about 7.5 horsepower pumps per 100 tons of peak block load. Instead of, kind of worrying about very large swings in demand, you know, switching it back and forth very, very quickly. Really try instead to kind of run it slowly, seasonally, have it be the tortoise, and then have your supplemental system kick in if you have to reach those extra peaks. Another way to reduce some of the pumping energy is to look at the glycol mixture. It's more viscous, it's more syrupy, it's harder to pump through. Of course, the higher the percentage of, say, brine or antifreeze you have in there, then the colder it can be and the less you have to worry about, especially in a cold environment like, you know, Haley or Ketchum, that it might freeze. But as you increase that, realize that it's going to have an effect on trying to push that more syrupy liquid through all of those coils. So you can upsize the pipes as one way to cut down on some of that friction. And that is going to have a higher initial cost, but you will save on operational use. It will reduce your pumping energy. Sorry, let me just get my mouse here together. Yeah, I already mentioned kind of the antifreeze, but look at both kind of full load and part load efficiencies. If these pumps are maybe sized for one particular load and instead they're operating somewhere else on the pump curve, they might be in a really inefficient region. So this really kind of comes down into the design of the system and why I think hourly simulation is really important to make sure that you're accounting for you know, how these are actually going to be used all year round at a variety of different conditions and studied. Some other notes is to use some different control strategies, how you're staging this with your supplemental equipment. Are you driving the pumps unnecessarily? Could you put them, you know, before or after that supplemental system, so that you're not asking as much of the ground loop? And then use it to, say, pre-cool or preheat some of the other supplemental equipment in there. Yeah, I'm gonna just kind of pass. Well, I'll mention this a little bit. You can also do direct distribution of boiler water, basically keeping some of the coils a little bit separate, if you will, rather than having everything run through the same system. So if you've got kind of a perimeter radiant system that you're running off of your domestic hot water, you know, keep it running at that high temperature and use your supplemental equipment to do that, rather than ask that ground loop to be running constantly and shifting that whole loop temperature up to meet those perimeter heating needs. And then ensure adequate, you know, return air. So if you are installing a heat pump system, you know, the biggest driver of its load is trying to heat up this air that you're distributing through the house. Well, this might be a good situation for an ERV or an HRV, a heat recovery ventilator. And then you get to reduce the load, the ask that you're making of those indoor coils, and require maybe less pumping energy there. And during the summertime, make sure that you're employing an economizer. So any free cooling that we can get from the outdoor air, you know, it's early in the morning and you know, basically the idea of opening up those windows, if you will, to cool down surfaces. An economizer is a more fancy automated way of doing that through your traditional HVAC system. Instead of asking your heat pump to cool that air down, you're just going to rely on that outdoor air directly whenever possible. All right, so some other kind of design strategies. I mentioned this initially, but a test bore can really help determine the number of boreholes that are going to be needed and develop a more accurate model. because the thermal conductivity can vary by location as well as diffusivity. And even just a couple degrees of temperature or a fraction of the conductivity can really change the number of boreholes that might have been initially designed. Make sure that the engineers are doing their homeworks and are doing their homework and really have confidence in their model and not just relying on rule of thumb. The whole idea of a hybrid system is to make it as small as possible. So make sure that we're incorporating, each of these different factors in building design: insulation level, lighting power density, plug load, all of these features, and not just rule of thumb, but making it very, very specific to this site so that you are not adding basically extra installation cost to these. Because as soon as you start downsizing that external area, that's when these become economically feasible, and that's the power of a hybrid system. And the more work that's done on creating those, this could be an energy model. It could also just be, the engineering heat load model. It doesn't have to be, a full-on energy plus, but as long as all of these factors are being built into it, then you don't have to worry about adding all of those extra safety factors, and then you can downsize your equipment. You might be able to downsize your pumps or maybe reduce the flow so you're not trying to push as much water through all the time. There's a lot of tools out there. They're pretty specialized, and kind of the more information that you have on the site and the ground, the better. I highly recommend seeking out this expertise. One good resource, if you're ever curious, is this geothermal heating and cooling design of ground source heat pump systems. We've got that here in our office, and you are welcome to borrow it through Idaho Power's tool loan library. This came out in 2016, and it's a really fantastic resource. Maybe a little more on the engineering heavy side, but pretty readable, and I would recommend it. All right, so let's talk about kind of the heart of the matter, economics, because these systems are not going to get installed if there's not a payback there. So a hybrid system can significantly reduce first costs, even adding in the supplemental equipment. This was one case study that came out of the Energy Center of Wisconsin. Adding a cooling tower, yeah, it did increase the cost a little bit, but they downsized their ground loops so much that in terms of millions of dollars, they saved pretty significantly. And by reducing their total first costs, that saved them kind of in the long term on their payback. I'm going to skip this slide so we can look at something that's a little easier to see on the computer screen. So this is looking at the total life cycle costs and savings for a traditional ground source heat pump system sized to the full load versus a hybrid system. In one of these cases, the tobacco lofts, there was no payback for the ground source heat pump, not after 20 years. It might have been operating more efficiently, but over the lifespan, it still cost too much upfront to make that money back. At Cashman, it turned out to be about even. But for every single one of these sites, the hybrid system did end up with a significant 20-year savings in terms of dollars per square foot. Right, so that's kind of the power of it, is by substantially lowering your first costs, and yet you're still using that ground source for basically 95% of the time. You're just not worried about that extra, say, 5% peak. So how do you actually figure out how big should my supplemental system be versus my ground source? I would highly recommend this study. The title is not super reader friendly, right? A methodology and computerized approach for optimizing hybrid ground source heat pump design. I have it here. I am happy to share it because it is actually very readable and I think very, very practical. So what they look at is, should we just be using rule of thumb? Traditionally, this lecture was initially developed by saying, size for just the smaller of your two loads, size for just the cooling or just the heating. Another rule of thumb out there is look at just, say, 70% or maybe 60%. But those are rules of thumb. So let's get a little more scientific about it. How do we actually optimize it? If we look at our peak cooling load in this example, I realize here we'd be more looking at our peak heating load. We can get a sense of, okay, how much do we actually want to cut off, and the number of hours that we're going to end up where we're not going to be able to reach that peak with our current system. There are formulas within that table. We won't have to get into any of that. I won't force you to do that. But by using those formulas, you can develop these curves where you're looking at your initial costs, which increase the larger the system gets, and then the net present value, looking at both kind of operation versus initial cost of the system. So what we want to do is find this low point, essentially, if you will. Come down here, and this is going to give us our alpha, essentially, which is going to influence this formula here for exactly what percentage should we be looking at for the percentage of heating load that we should be sizing for. In this scenario, they found that a 60% peak capacity could meet 82 to 96% of the annual demand. By using this optimization technique, they found that they could reduce their payback period up to 12, all the way up to 12 years over a conventional system. And then if you were to use just a ground source heat pump, this would be a 19-year payback. So looking pretty close at end of equipment life. Pretty tough to argue that on an economic standpoint. If you looked at just kind of rule of thumb, which was like sizing for just the smaller of the two loads, then you would end up with a 17-year payback. But by optimizing your system, the payback was cut by 5 years. Very, very significant, and so the difference in payback period versus that traditional rule of thumb, they looked at a few different facilities for both heating and or cooling dominant, and the change, this is just the difference in payback period between one hybrid ground source heat pump system and an optimized hybrid ground source heat pump system, was quite significant, 3 to 7 years. In some situations, it made less of a difference, but a full year payback, is certainly might make the difference between a go or no go on whether or not to install one of these systems. So just to emphasize this again, the smaller the system, the cheaper it's going to be up front. So yes, we can work on all of that optimization, but before we even get there, it's our role as designers, as architects, as well as engineers, to reduce the loads as much as possible during the design phase. So, reduce envelope leakage, upsize our insulation a little bit so that we don't have to drill as many boreholes. Really maximize the controls that we have in terms of thermostat set points and setbacks in the office, and install motorized dampers so we're not getting extra cold winter air when it's not needed. All right, so that's all kind of on the design phase. and we have a lot of opportunities here. So the more we can kind of integrate the architecture and the engineering, the more that the payback period is going to be smaller and will make more sense. So just kind of wrapping up, using a hybrid system is going to reduce the payback period over a traditional ground source heat pump by 20 to 40%. It's really economical for multifamily or hotels and heating dominated climates. I think that's why it's being used in a new design up there right now. They can also link with your VRF system, and you've got a lot of zoning opportunities. So each room can have its own thermostat, which is very helpful. It's one of the advantages of VRF as well as any heat pump system. But it takes a lot of homework. It takes a lot of time up front to downsize your loads as much as possible up front, right? Really work on minimizing those loads. And then do the calculations, look at the soil conductivity, look at the size of the piping that's going to be in there, the pumping load that's going to be all year long, to size the hybrid system correctly, whatever supplemental system that might be. Anyway, that's what I've got for you today. There's about 10 minutes for questions. I'd love to have more of a dialogue and hear more from you, but I appreciate your time today, so thank you. And feel free to unmute yourself. I think Dylan will, no, I think I will be able to launch a poll here. Yeah, so feel free to fill this out. Oh, let me look at the chat window really quick before I do that. Chat. All right, so I'm going to launch polling while I answer this question. So feel free to, minimize that or answer it in the background at some point. So just reading this for the sake of those that are listening. Antonio, thanks for the question. I mentioned that I have a study that I was talking about the methodology. Do I have a PDF file or can send that out as a link? I do have a PDF file, so yeah, feel free to email me. My email's on the screen there. I'll also see if I can talk to my IT person and get your email and send it your way as well. So I'm just making a note of that. But it is a very helpful study. There are some other local folks. There's a lot of people in Colorado working on this as well. But there's some local trainings available from, say, like Half Moon Education or other seminars on geothermal. I found going through those kind of all-day workshops very helpful in terms of just increasing my own awareness and knowledge of things like gophers and how they can be an issue and how deep these systems should be. One thing I didn't mention, I'm just going to continue talking a little bit till I see something. I'll mention one anecdote, which is soil saturation has a huge impact on the conductivity and the amount of heat that you're able to extract from your system. So if you have a dry soil, if it's below 25% saturated, it's almost impossible to make an economic case for it. As soon as you get above 25% and even to 50%, then your thermal conductivity is pretty well known, and it doesn't vary a lot, even from 50% saturated all the way up to 100% saturated. You're looking really good in terms of conductivity and your ability to move heat from the ground. And once it freezes up during the winter, that's a pretty steady conductivity as well. But if you don't have a high water table, if you've got super deserty, dry, sandy soil and no irrigation to speak of whatsoever. Once again, I'm not a hydrogeologist, so this is for their expertise. But once you get into a 25% or lower